Okay, let's start. Types of bonds. What do you remember about the types of bonds that you learned in regular chemistry?
Ionic, covalent.
Okay, so we're going to start with, let's start with ionic. How can you tell if something is an ionic bond? You can tell by looking at its formula. What does the first thing have to be in order for it to be an ionic bond?
Metal.
It's a metal plus a non-metal. But the non-metal bit could also be a polyatomic ion. And so if that thing at the end of your compound is a polyatomic ion, it means that it has a charge. An ionic bond is characterized by ionic charge attraction. So the metal is always the thing that has a positive charge, and the non-metal or your polyatomic ion always has a negative charge. The positive thing has to come first. That's why your compounds will start with a metal. It is not possible for metals to have a negative charge. Okay. The next type of bond after the ionic bond is what we call a polar covalent bond. A polar covalent bond is where electrons are shared, but they're shared so unevenly that poles are created within the molecule. A really good example of, I'm going to write, electrons are shared, but unevenly. A really good example of a polar covalent molecule is water. It has this bent shape like this because oxygen is much more electronegative. That means that when it shares these electrons with hydrogen, it will want the electrons more. It the electrons gravitate more to the oxygen than to the hydrogen. And so this causes what we call a pole. Have you ever seen this symbol before?
No.
It is lowercase Greek sigma. Oh wait, or delta. No, it's delta. It's delta. I'm sorry. Sigma is something different. It's lowercase Greek delta, and it means partial. So the symbol indicates that you have a partially positive end on this part of the molecule and this part of the molecule as well. So then where is the negative end? It's up here at the top where all of those electrons are hanging out. So why the partial and not just a plus and a minus? Because the electrons aren't always here. Just like they're not always gone from this place. They're sometimes there. And so that just makes the magnet much weaker than it would be for an ion. In a little bit, I'll show you how to distinguish between all of these things. I'm just going to give you the definitions first, and then I will give you the little foolproof way to always know what the answer is. That's polar covalent. And then there's moderately covalent. Sorry, I forgot a word in there. Moderately polar covalent. Got ahead of myself. Which is what it sounds like. So it's a little bit less of a unequal sharing than polar covalent. So they're shared more evenly. But not perfectly. If electrons are shared perfectly, it almost always means that they're shared by the same type of element. So I'm going to skip right away into the last one, the pure covalent. And the best example is when you have two elements that are the same that are sharing electrons. Like, I'm just going to write here equal sharing. Any of the diatomic elements. Do you remember what a diatomic element means? Diatomic means what it says, di meaning two, atomic meaning atom. And so the elements that form diatomic elements are these things. If you were to draw your Lewis dot structure for chlorine, it would look like this. And because chlorine is equally electronegative as this chlorine, they both want the electrons equally, and so the electrons are always in the same place in the molecule. And so there isn't this type of hole that's formed because the molecule is sharing the electrons evenly. This is tricky to understand, but there is a really simple way to know which kind of thing you have. I'm going to write it actually on the whiteboard because we're going to probably need it later on, and then it'll always be up. So find a nice place to put this in your notes. It's a number line. We're going to start at 0. That maybe is not enough space for me. And then we're going to end like at 2 over here. So like try to evenly space out 0.5s. So here's my middle, maybe 0.5, 1.5. Okay. Do you have your periodic table out, the one that I gave you? Flip it over and look at the back side where it says electronegativities and oxidation states.
Which one?
The one that my made one. The one that I made. So you're going to want to use this side, the one that says electronegativities and common oxidation states. Recall from, did we do this? Maybe, I don't remember. The number, okay, so find carbon. The number 2.55 is carbon's electronegativity. That's its actual number. There's another place you could find that electronegativity, obviously ChatGPT, but in your calculator, if you have the light up ones, in your app that gives you the periodic table, all of those electronegativity values are listed. Okay, so what you're going to do is you're going to plot on your number line for whichever compound you're looking at the electronegativity difference. But we need the absolute value. Notice how the number line does not go below 0. It's a hard stop at 0. So if you do a subtraction, you get a negative number, take the absolute value and use the positive value. I'm going to write that here, absolute value. Okay, so this is the rule. Between 0 and 0.5, you have a purely covalent bond. So if you have a carbon-carbon bond, how would you calculate the electronegativity difference? 2.55 minus 2.555 is 0. And so it's in this region here. You can maybe write 0 to 0.5 if you want. Hopefully you can see that. I've got a lot of crap. I'm really sorry. You gotta go, buddy. And then the next section is between 0.5 and 0.9. This section here is what we call moderately covalent. or moderately polar covalent. These green markers really smell bad, but kind of in a good way, you know what I mean? And then between 0.9 and 1.7, you have your polar covalent. Everything after 1.7, 1.7 to whatever the biggest number difference could be, those are your ionic bonds. This is the most demystifying of all the things. If you can quantify something and put it on a little number line, it makes it easy.
Say the numbers again because I can't really see it.
Oh, sure. Oh, that's right. Because when I write on here, there's a grid.
What is red?
The red is 0.9 to 1.7.
No, what is it?
Oh, polar covalent. Thank you for asking, Hayden. I'm sorry. So the number values are 0 to 0.5, 0.5, oh, I didn't even write it here, 0.5 to 0.9 for moderately polar covalent, 0.9 to 1.7 for polar covalent, and 1.7 and up for ionic. I took every bond that I knew what it was, like just from knowing, and I did the calculations, and so I came up with this. I have never seen this any other place. That's why I think that this is completely demystifying. You can simply do a little bit of math, and you always will have electronegativities because you will always have that app on your calculator for like when you get to the AP test. If you always are able to calculate this, and then what we'll do is we'll put these little cheat sheets in your calculator, so if you don't have it memorized or if you forget, you're able to look at it and find it. But if you can plot this somewhere on your number line, you're good to go. It's easy to decide then. So I think I'm going to give you your homework now, and let's just do a couple of examples because I really want you to be able to.
Who sits on the
I don't know why.
That one's my last one.
What is it? Oh,
David sits. Or not David.
Yeah, David was a chew.
Gladys is there too, but
I know it's a trade, but we didn't.
who's just
So that had been
okay, this looks terrible. That's
that
not
had been just
really.
one.
Does it feel really sensitive?
sure you were, David.
Yeah, yeah, yeah. Yep.
David is the
Ooh.
little pisser, bro.
Okay, just be careful with that. Yes, go.
I know it's David. David.
Okay, Demetrius, here you go, buddy. Sorry. All right, let's look at some of these. You can find the electronegativities, right? Let's do the first one where it says CAS. Okay, so calcium's electronegativity is 1.00, and sulfur's is 2.58. So your difference is, well, if you did this math, it would be negative, but remember, it's absolute value. So 1.58 is a polar covalent. Now this is really high. That's really close. We know that calcium is a metal, and so I would look at this and I would say that's an ionic bond. And so if you wrote down ionic as well, I would accept that because it is a metal. It's just that the attraction isn't as great. I'm only going to do one more of these to show you how easy it is. And this is letter C. Now, CH4 is my compound. Every single one of the carbon-hydrogen bonds are the same, so you don't need to do it 4 times, just do it 1 time. Carbon is 2.55, and hydrogen is 2.18. So when you do that math, your answer should be 0.32? Or is that wrong? 0.27. I went the wrong direction. Thank you. 3.7. Oh, brother. It has been such a day. I don't know what made me think I could do mental math. But here we are. So what kind of compound, or what kind of bond would this be? Pure covalent. Yep. So all you need to do for this one, you can do this math on your calculator or in your head if you're better at it than me. But next to this compound, just write C for pure covalent. That's the only work you need to show.
Wait, you just need to write C?
Yeah. Or whatever the answer is. But it tells you like in the question what the abbreviations are, so you don't have to write words. Okay, let's see. Is there anything else that I have to tell you in that section? No. I have 3. All right, 2.2. 2.2 is called the intramolecular force and potential energy. Okay, the word intramolecular means that you're talking about what's happening inside a molecule. Not what's happening between 2 molecules, but what's happening inside the molecule itself. So, we have that as our little definition. There are just a couple of terms you need to know to help you to understand the concepts in this unit. The first term is what we call bond order. This is so simple, you guys. Bond order is the number of electron pairs 2 atoms are sharing. And the answer, the options for bond order are either first order, second order, or third order. That's it. So a single bond is what we call a first order. A double bond is what we call a second order. And so a triple bond should be called a, there it is. Okay, easy, right? So how do you know what the bond order is? You have to draw yourself a Lewis dot structure so that you can know how much electron sharing is taking place. So remember that when you're drawing a Lewis dot structure, 1 line equals 2 electrons. In other words, an electron pair. Okay, so that's your bond order. That's the first term. The second term, there are 3 terms, is bond energy. This is also really easy to determine. The higher the bond order, So remember, the higher the number of electrons that are being shared between those two atoms, the higher the bond order, the more energy is needed to break the bond. I might have an idea for a demo here. Of course, I don't have any rubber bands. Okay, so imagine this in your mind's eye. You have one thin rubber band, and you're stretching it until it breaks. Not too hard. One rubber band, you stretch it, and it breaks. The more rubber bands, though, you put on between your fingers, the harder it is to pull them apart, right? Same thing with the bonds. The more electrons that they're sharing together, the harder it is to break them apart. You have to just add more and more energy.
No.
Put your shoes on. No dogs out in the lab.
My shoes are.
Are the dogs out?
No.
Okay.
Yes.
Well, they're like. Yeah.
Put your shoes on, Jared.
What about the other one? I can't put it on when you.
The third and final term is bond length. It's also related to the bond order. The higher the bond order, well, there are two bits. The higher the bond order, sometimes people abbreviate bond order as BO. The higher the bond order, the shorter the bond.
What did you say?
So that's one way to determine length, but there's another. The smaller the atoms, the shorter the bond. And that makes sense because if your atoms aren't taking up very much space, their electron clouds aren't either. And so that means that the electrons that are being shared in the cloud aren't overlapping as, like there's a smaller space in between those. All right, look at your homework and look on the second page on page 3. This question says, in each pair of bonds, circle the one that is shorter. So in all of these bonds, there's always something that stays the same. In part A, so this is number 3, part A, we're comparing the bond length between boron and chlorine and between gallium and chlorine. So chlorine is staying the same, but boron and gallium are different. So if I just said the smaller the atoms, the shorter the bond, we need to figure out which one of these two, okay, it wants us to know the shorter one. So which one of these two atoms is smaller? Use your periodic table trends. Boron is here and gallium is here, so which one is smaller?
Boron.
Boron, so that's the one you'll circle. So for number 3, all the work that you need to do is literally a circle. And that's just based on the atomic size trend. Or, oh yes, and I didn't do any comparing between like a C single and a C double bond. So that should be something that's easy for you to do. Not too time consuming, it's just a circle. Any questions about that?
Yeah, I didn't understand.
Which one of these two elements is smaller?
Wait, then what happens when this?
Boron or gallium? Which one is smaller?
I mean, the number is smaller. 1
No, it's not. You have to use the periodic table trends. As you go down a group, you get bigger.
Oh, God, yeah.
And so boron is, that's how,
Yeah.
not using numbers. Don't ever use numbers to determine size. Use your periodic trends.
So,
The further is to the right, the further up.
Yes, the closer you are to helium, the smaller your element is, because he's the smallest,
Okay.
size-wise.
Okay.
Okay, that's all of 2.2. 2.3.
We got 2 more.
Yep. And 2.3 isn't too bad. What I want to do, this is called the structure of ions, I think. Ionic solids. First, I'm going to give you some tips for answering MCQ questions, and then I'm just going to teach you what lattice energy is, and then we'll go to 2.4. Okay, so when you're solving MCQ questions and there are pictures, you have to look really carefully at the details of a picture. So if you were asked to compare these two pictures, which is the smaller, left or right, of these two positively charged ions? Who votes for left? Who votes for right? Which one is smaller? Like, it actually means the size. This one is smaller. Which one is smaller? The one on the left. So you have to pay attention to like the little details. Now there is a question involving density. You maybe don't need to copy this down, but lock in and pay attention to this. Because it's a lot of tedious writing. Okay, so here's one array. An array is a pictorial representation of what the ions are looking like. Here's one array. Now I'm using the same size, or I'm going to attempt to use the same size of positive ions, but now I have a bigger negative ion. And my question is going to be, which one of these two arrays, which one of the pictures, has a more densely packed depiction?
Right.
The left or the right? Who votes for left? Who votes for right? The denser one is the one on the right. Why? Because these ones are so much bigger. I tried my best to make it look like spatially accurate, but we know I'm spatially deficient. So, because these negative ones are so big, they're going to take up more space, which means they're going to be more dense. So this one is more dense. When you get to, hi Lily. When you get to these questions on your MCQ, if you're working on it on Friday and I'm not here to answer your questions, go to the website and look at my notes that I made for you, and you'll be able to see this in a much better look. I did a better job because I could take my time and it looks more nicer. So this is more dense. And then the last thing that I wanted to point out to you is that unless you're adding energy to the system, things of the same charge don't sit next to each other. Unless you're adding a lot of energy, unless you're forcing them to behave, they will not sit next to each other. So if those of you have siblings who are like really out of control, like how likely is it for them to sit in a row right next to each other and be silent for 50 minutes? Like, not likely. You have to add a lot of energy. You have to do a lot of crowd control to make this happen. And so unless you are adding a lot of energy, that will not happen. Elliot? Oh,
What if you can't even sit down?
I have an example.
yeah, then that's a bit. Yes, you have an example, Elliot? Let me hear it.
No, I can't.
Okay.
No,
It's too bad?
yeah,
Like APU.
I don't think I can say it.
Okay, after I turn the video off and save that. Okay, and then the last thing I want to tell you in section 2.3 is this concept called lattice energy. Lattice energy. Okay, so to teach you what this is, I'm going to show you what Coulomb's law is. Oh, I spelled it wrong. Coulomb's law talks about the force that's involved when two oppositely charged things are next to each other. And so I just have to, guys, stop talking. This is a constant. It's your Coulomb's law constant. But this is the part that's actually what we are interested in. Okay, so what do you need to know about Coulomb's law? You don't need to know how to use it. You just need to know how to apply it. So we're not going to do any calculations. I'm just showing it to you here because if I don't write something down in its entirety, it makes my mind hurt. God bless you. Q1 and Q2 are the charges of your positive and negative ions respectively. And so that's always going to be a whole number, +1, +2, -1, -2, etc. R is the radius between, so it's the distance between the two atoms. E is your lattice energy. It's the energy required to separate the charges. So if you understand how fractions and math work, you understand how Coulomb's law works. Greater charge, a greater numerator, means a higher lattice energy. Right? That makes sense to us mathematically. If we're putting a number on the top of a fraction, that's increasing the magnitude of the result of the math, whatever math there is. How do you get your energy to be higher? How do you make this number bigger by changing R, though?
It has to be smaller.
Yes. The closer those ions are to each other, the more energy is required to break them apart. Smaller distances, smaller radii equals higher lattice energy. So what does that mean? It means that your really big fat atoms, like your francium and your radium, are going to be really bad at this because they're big atoms. And so if you want to have a stronger ionic attraction, you're going to choose something that is a smaller person, maybe that looks like francium, like maybe lithium or sodium, because it's spatially smaller. It'll be more stable if you can minimize that distance. Does that make sense? I'm going to lift this up a little bit, give you a chance to finish copying that. And then I have 2 more definitions for you for the last section, and then that's it.
Hey, can you scroll up just a little bit?
Oh, sure.
Okay.
So, are you gonna use this?
No, you don't need to know how to use this equation. You'll never do this math. You just need to know how to apply it. And there are a couple of MCQ questions that will help you to know what that means. Elliot? Re-explain it? Certainly. These are your charges. Energy is the amount of energy that's required to separate the two ions. And so, I don't have like any. Let me get something that looks like an atom. Hang on.
And then if it's divided, it's here, so it's polar.
My ball box. God bless you. All right, so let's imagine that these are two atoms. They're the same thing. So they're two atoms of the same element. The distance, the radius that we're going to measure is between the middle of both of them. And so this would be my radius. As that radius gets bigger, the denominator is getting bigger. And so as your denominator of a fraction gets bigger, that number will get smaller. So it'll become easier to separate these two balls than it would be these two balls. But wait for it. I can't get it open. If I had an atom that was this size next to this one, that would be even harder to separate because this one is so much smaller than the one before. The distance that you're measuring, remember, is between the middles of both of them. So this has a smaller radius than these two. Now, radius is actually a distance that you're measuring. Charge is determined based on like who the element is. And so some things are determined based on where they are in the periodic table. If you're in the column 2A, what is your charge? You're a 2+ charge. Okay, so let's compare calcium chloride and sodium chloride. Calcium has a charge of 2+. Chlorine is a 1-. Sodium is a 1+. Chlorine is still a 1-. If you're just using these pure numbers, 2 times 1 is 2, right? And 1 times 1 is 1. And so if you're comparing these two pure numbers, you'll have a 2 versus a 1 as the numerator. As this number gets bigger, your E also goes up. So what does that, how do we explain that chemically? It means that the bigger the charge, the stronger the magnet for other things. There's nothing wrong with a +1 charge atom. That doesn't mean that it's bad at being an ion. It just is who it is. And not always are we concerned with what this concept of lattice energy. But if you're trying to make a compound, or if you're trying to, let's say that you decide to really like chemistry a lot in college and you decide to be a polymer chemist, or a like nanotechnology chemist, where you are making materials that have never been created before. If you want something that's not easily broken or manipulated in any way, you want to try to make sure that the energy that it takes to separate things is the greatest amount possible, because it lends to the strength of the material. So that's why it's like something that we would care about. So you don't need to know how to make the calculations. You don't need to know how to figure out what the Q's or the R are. You just have to know how to apply it. And there are some questions on the MCQ that will help you to understand what it means to apply that concept. So try your best on those. If you haven't gone back to look, you'll notice that when you get a question wrong on the MCQ and you go back to look into your score, AP will tell you why you got it wrong and why your answer is not the correct one. that can really be helpful. But if you're ever curious about that or their explanation doesn't make sense, bring it to me and I'll talk you through it. All right, last one. 2.4. What's it called? Structures of metals and alloys. I said that I have 2 definitions for you, but I kind of have 3. Does anybody know what an alloy is?
Isn't it like a mix of metals?
Yeah, it is. It is. It's a metal mixture. Does anybody know of an example of an alloy?
Brass.
Brass is an excellent example. Any of your like carbon steel, that's an alloy. Anything that's a metal that's not a pure element is an alloy. Stainless steel is an alloy, yep.
So actually, some of or jewelry is like alloy.
It is, yep. Yeah, unless you have 24 karat gold, which you would never wear as a jewelry because it's very incredibly soft. And like 24 karat gold is like the only heavy metal that you can consume in your body. And so like just gonna press pause here on the I just didn't want to say that on the video. Okay, so an alloy is a metal mixture. There are 2 kinds of alloys I just need to talk to you about. The first is called interstitial, and I need to look at my notes to know how to spell it.
There's brass.
Interstitial alloy. An alloy where small atoms, and I just like kind of like spoiled the fun, but the carbon steel or the carbon fiber alloys are a kind of interstitial alloy. It's often carbon that's used, like the small atom. What do we mean, like small in size? So carbon is very close to helium, and so that makes sense that it would be used. An alloy where small atoms are placed in the, wait for it, spelling help, stices, they're the small spaces between the other metal of like the main metal. I'll draw you a picture. Okay, so imagine that we have carbon steel. And so iron is the main element that is an actual metal. And so it's in an array, something that looks like this perhaps. Oops, that's an E. And so then how do you make carbon steel? You put little carbon atoms. So carbon we're going to pretend is green. You put carbon atoms in the interstices. Those are the little spaces in between, the interspaces, so that you are going to add strength and durability. Adds durability. Oh boy. The math and the spelling are going. That's how you know I'm sleep deprived. Adds durability and hardness. So by changing the chemistry of the metal, by putting these other atoms in between it, you can change the physical characteristics as well. That's what we call an interstitial alloy. Okay, so are we done writing that?
No.
Does anybody? Okay. The other type of alloy is what we call a substitutional alloy. And it is what it sounds like. So the interstitial alloy, you know that it's if you can remember what interstices means, you can remember what an interstitial alloy is. Because interstitials is the little spaces in between. And so if you can put something small into those little small spaces, interstitial alloy. You don't need to have these words memorized, but you need to be able to like not freak out when you see them on an MCQ. So substitution, what does it mean when you substitute? It means you put one thing in for something else. So a similarly sized metal atom is substituted for what we call the host metal. The purpose of creating a substitutional alloy is that it decreases corrosiveness. Do you remember what it means for something to be corrosive? It reacts with acids. Decreases corrosiveness and the second thing I forgot. Oh! Improves conductivity. Do you know what conductivity is?
Meaning it conducts electricity.
Yes. Where would be a situation where you would want to have better conductivity?
Wires.
Yeah. Yep.
You know what?
If you're trying to create a battery for like an electric car or something, to be able to transfer your power, your electricity in a way where it's not lost to the environment is a good thing, because then you can go farther on the same amount of charge. All right, you still have 15 minutes left of class. If you feel like working on your homework, you can. The last two questions I'm not going to teach you because I spent 4 class periods teaching you this, except for Bella, when you were in regular chemistry.